in the video where we introduced the atom, I went off a bit about how at the center of an atom we have the nucleus, and it's actually a very small fraction of the total volume of the atom. And the electron, even though we call it a particle, it can really be best described as kind of a smear around this nucleus. That although it's a particle, because of the Heisenberg uncertainty principle, we can never tell exactly at a given moment where the particle is and what its momentum is. So to describe it as a particle is a little bit, I don't know, at best it's a little bit strange. And we said that the way that they describe it, they don't say that this particle is in an orbit, like the planets around the sun. An orbit would be like like that. That would be like the orbit of Halley's comet around the sun. Instead, it can be described as a probability function around the nucleus. So if the nucleus is there, we have one orbital, actually the 1s orbital, and we'll talk about that in this video. It'll be a sphere. I felt like saying sphere. A sphere around the nucleus. And actually the sphere has no strict boundary. Whenever you see someone draw it, they're just saying where's 90% of the time the electron going to be, and then they'll cut off a boundary and they'll say, okay, it's going to be within this sphere, and actually it gets denser as you get into the center of the sphere. So if this was a cross section, it would be really dense in the center, and it gets less dense as you go outside, which just means that there's a much higher probability of finding the electron in the 1s orbital near the center than near the outside. Although this boundary point out here is just artificial. You can find the electron pretty much anywhere. It just has a much lower probability out there than in here. But I'll touch on that in more detail in the rest of this video. But I wanted to go back to the Bohr model, and the Bohr model is the kind of, let me write that down, Bohr model. And sometimes it's nice to know it's named after Niels Bohr. And his model of the, and don't think that this guy was some slouch. He was at the cutting edge. And this wasn't even that long ago. This was roughly about 100 years ago. So already we're talking about things that you can, probably dig up research papers in your library not too long ago where people are debating some of these issues. But in the Bohr model, that's the model where he kind of modeled electrons as planets revolving around a star, around the sun. And that model is actually useful, at least it's useful in my brain, to conceptualize the idea of energy state. So if this is an electron around the nucleus, right? It's moving around like in an orbit, and we know, and I want to emphasize, orbits aren't really what happen. Orbitals are what happen, and orbitals are more like probability functions as to where you might find an electron, while an orbit is a very kind of classical mechanical way of describing the path of a classical object, like a planet around the star. I don't want to say the analogy too much. But if you view this model, the idea of energy levels start to make sense. For example, if I have something orbiting, if I have a planet orbiting a star like that, and if it were to have more energy, perhaps its orbit would become more elliptical. Maybe, if for some reason I put some more energy into this. I had like a little rocket booster on this planet right now that temporarily put some energy into it. Instead of going down this path, maybe it'll push it this way, and maybe it'll accelerate it a little bit faster, and maybe it'll go like a path something like this. I don't know. I haven't done the math. But in general, it's going to have a little bit higher kinetic energy, so it's going to get a little bit further away from the planet. And then maybe if I rocket boosted it again, its path would look something like this. Its orbit would get further pushed out, and as it approaches the planet, actually would achieve faster speeds as it approaches the planet with gravity. And there's a couple of interesting things here. One, obviously, the planet or the rocket that has this orbit has more energy. This one right here will have more energy. More energy than, let's say, this one over here. And energy is this, even though we're talking in the quantum world, and this is just an analogy because we know orbits don't really apply, but energy is really the same energy that we talk about in anything. And energy is the ability to do work or transmit heat or create heat. So, if you're not doing work and you have energy, you might kind of waste the work by generating heat. And we'll talk more about that in future videos. But it's the same idea, right? If I had a little rocket pack and put some energy into this or pushed it somehow, I might get into this higher orbit. The idea of orbitals is the same thing, except obviously they aren't these well-defined paths. That as electrons get more energy, and that energy can be given to the electron mainly through light waves or electromagnetic waves can be put onto the electron. And when we do quantum mechanics, we'll do that in more detail. But essentially, if you view light as a bunch of packets, as a bunch of photons, and a photon hits an electron in a certain energy state, all of a sudden it will enter a higher energy state. A higher energy state, and maybe it'll go to this probability distribution that's a shell around that one. And maybe if after it gets excited, and these are words that you hear physicists and chemists say a lot, but excited just means that energy was put into the electron and it went to a higher energy state. And it might stay there, or it might just want to go back to its lower energy state. So when it goes back to its lower energy state, it would emit the photon back, and that's actually why you see some things sometimes glow. But we'll talk more about that in the future as well. But I really want to give this intuitive point, because in the rest of chemistry and a lot of physics, people talk a lot about energy states, or the electron going into a higher or lower energy state. And that's just the general idea, is that an electron in a kind of higher orbital has had energy put into it, although it wants to get back to its lower orbital. Now you might ask, well, how can an electron stay in a higher orbital? For example, what if an electron just stayed, what if we already had 2 electrons in this orbital over here? And we'll talk a little bit about how the electrons, the different orbitals get filled. But I want to give you the intuition first. Let's say you had 2 electrons that, they're just all over this place. You can't even pinpoint them. And then I were to add a 3rd electron. So you might say, oh, the lowest energy state is this magenta inner sphere that I just drew. Why wouldn't that 3rd electron go there? Well, my intuition is that, well, there's already 2 electrons there, and although the electrons are attracted to the nucleus, because the nucleus has all the positive charge in it and the electrons have all the negative charge, it's repelled by these 2 electrons, because negative like charges repel each other. So it will want to stay away from these 2 electrons. And so it'll go to the next energy state. It'll maybe go into this shell out here. And the other interesting thing about energy states, and this is key to chemistry when we start talking about reactivity and how something might react with something else and why would it, is that things at a high energy state, for example, if we use the orbit analogy, this high energy state, they get further from, in the case of planets, they get further from the body that they are kind of attracted to, so the gravitational force is weaker. Or in the case of electrons, when they get further away from a high energy state, the Coulomb force is weaker, right? The charges we talk about when we talk about electrons and protons, those are the Coulomb force. So there's a negative charge, and then you have a positive charges in the center. But it gets further away, I guess is the best way to think about it. And so the force from the nucleus is weaker, so they're easier to pluck off. They're easier to pluck off and maybe share with other atoms, or maybe to give to other atoms, and we'll talk a lot about that when we talk about bonding. But I wanted to give you this intuition first. So the next question that might arise is, well, so how do the electrons fill the different orbitals, and what do those orbitals actually look like? And I've cut and pasted some interesting graphics from Wikipedia. So here are the orbitals. Here are the different orbitals. And so there's 2 aspects to the orbital. One is its shell, its energy shell, and that's given by this number here, n. That's the energy shell. And just so you know, I mean, everything kind of fits together. Those energy shells correspond to periods in the periodic table. So a period on a periodic table is literally just a row in it. So this is period 1. Period 1 in the periodic table. Right there, all the way to helium. That's period 1. It's just the first row. And that means that the elements in that first period, that their electrons will fill the first energy shell. So for example, hydrogen. Hydrogen has 1 proton, and everything we do, we're going to assume neutral atoms. So we can take, we learned in the last video that the atomic number tells you how many protons there are. Right? This is how many protons there are in hydrogen. But if we assume it's a neutral atom, we can say that this is also the number of electrons. So we can use the atomic number also as an indicator of how many electrons in a neutral atom. So this has 1 electron. Where does it go? Well, it's in the first period, so it's going to go into the first energy shell. And so the first electron will go right here in the 1s energy shell. So if we wanted to write the electron configuration for hydrogen, we would write, so hydrogen, the electron configuration is just, it's in the first energy cell at 1s1, and there's only one electron there. And what does that first orbital subshell, that S shell, look like? It's just a sphere. It's actually what I just drew at the top of the videos. It's literally just a sphere, and if I were to draw a cross section of it, it gets denser in the center, and then it gets less dense as you go outside. And in the last video, I showed you what the helium, you could kind of say the orbital function looks like. And you saw it was really dark and dense in the middle, and it got more sparse and grayer and whiter as you went outside. So what does helium, what's helium's electron configuration? Well, in each of these subshells, and I'll be a little bit more specific in probably the next video because I'm pretty much out of time, you can put two, I guess in each of the geometric configurations for each subshell, you could put 2 electrons, and we'll do that in some detail in the future. So the configuration for helium is, it's in the first period, so it's 1s2. So in the S subshell within the first period, or the first energy shell, it has 2 electrons there. Fascinating. So what about lithium? Lithium, right here, also the name of a Evanescence song. I think it's the name of an Evanescence song because it's used to treat depression, or at least in the past it's been used to treat depression. So, lithium, what is its electron configuration? So the first electron goes into 1s1, the second electron goes into 1s2, and when I say the first or second, I'm saying energy state. So the first electron wants to go into the lowest energy state. That's in the s1. Then the second electron also wants to go there, and 2 electrons can fit in that first energy state, or that first suborbital, or that first shell, so then it becomes 1s2. Then lithium, it fills that first 1s2, it fills the first energy shell and that first subshell, which is the S shape. And so now it has to go to the second energy cell, and that works out relative to what I told you before, because it's in the second period. It's in the second period. The second period is that right there. Right? It's in the second period. So its electron configuration is going to be 1s2, 2 of its electrons filled just the way helium filled, and then its third electron will be 2s1. So that's its electron configuration. What do I mean by 2s1? Well, so lithium is going to have 2 electrons in that little dot that I overwrote it, and then around that dot there's another shell, which is the second energy shell, and it's going to have 1 electron in there. So let me see if I can draw that. So it's going to have one probability, I guess, sphere where the first 2 electrons are going to reside, and if this is a cross section, that third electron is going to reside in a probability shell around that. When I draw these, that's not like the electron is exactly there, the orbital. I'm just drawing where kind of you're just doing a cutoff where it says 90% chance of finding the electron. The electron could show up there or there or there, but this would be a very low probability, while right here would be a very, very high probability. Anyway, I'm out of time in this video. I'm going to continue this discussion in the next video, and I'll start talking about the more bizarro shapes that the orbitals can take on, and maybe give you a little intuition on why these shapes aren't really that bizarro.